Hello, this should be episode 1 of London's AP Chemistry, but technically there would be more episodes before this. This is slightly of an advanced topic, but it's the one I need to do to be able to get my assignment done for AP Chemistry. Sorry, Dr. Aker. Now, I will put this out there. What we're doing today is electron spectroscopy, or at least how does it work? How does it make sense? What is the point of it? How do you use this to understand atoms and elements and things of that sort better? Well, I'll explain to you. But I'm not quite going to do that without something to help me, because it's difficult to understand something just off somebody's words. So what I'm going to use is a notebook. Now, I know this may seem kind of basic, just pulling out a random notebook, but I need you to understand it's not that hard to understand. Now, electron spectroscopy, let me open up my pen here, is simple. It's all based on these graphs. Now, the graphs are in XY format, as you can see, and the thing with them is they are actually the photoelectron intensity, so I'm going to put P dot I, or really P dot E, whatever you feel like works best. But right there on the y-axis, we're going to go ahead and put Pi. Now, what that's talking about is the amount of photoelectrons it would take to break down a shell. I mean, I would need to explain this further, and you should understand there are shells, subshells, electrons, and things of that sort within this molecule. Now, let's see. It'd be best if I gave you an example. I apologize for the lapse of judgment. Let's say we were to do, and I have my periodic table right here, there will be one that appears on the screen, maybe in a few seconds. I'm going to do sulfur, okay? So if we look at sulfur, it is on the third row down, and it is in the A6 column, which I know it may not make sense, but the first two columns are called A's, and the right 6 are called B's as well. But then the 10 in the middle, where all those metals are called the B's, and it's to separate the valence electron normalities from the irregularities. Now, let's get something straight. I'm going to do sulfur here, so I'm going to have to go down 1s2, 2s2, 2p6, 3s2, 3p4. Okay, now if you didn't understand that, there are periodic table ways to understand how to do electron configuration, but that's not quite what we're covering in this video, so I'm not going to tack onto it too hardly. Just understand that the combination of electrons within electron shell and subshell are denoted on the periodic table. Although they may not be very obvious to the naked eye, they are there. The first two, hydrogen and helium, are together, then lithium, beryllium, then boron to neon, and it continues in that pattern until you get... So I'm not going to tack too hardly on that. I'm going to go back to the actual main point. We're doing sulfur here. So we're going to go down to 3p6, okay? So with photoelectron spectroscopy, right here, each wave will be different depending on what you're doing. Now, the first one we're going to do here is 1s. 1s is just going to be real small like this. And we're going to denote this as having 2 electrons, 2 points up. Okay? Now, the reason we're doing this is you have to show the waves differently for each individual thing, making sure you can see it there. This right here would be 1s2. But then what if we went over to do 2s2 or 2p6? Well, here's where the issue starts. See, whenever an atom has electrons, let's say we're doing this shape, for instance, an atom, in this case, we're doing sulfur, so I believe it's 16? Yes, it's 16 protons, okay? And we're going to do this, and then there's 2 over here, and we're only going to go out to here, but there's 8 electrons over here, right? So the first thing you need to understand is that the amount of force coming from a proton onto these electron shells is varying. See, the first electron shell, or subshell actually, will receive a much greater attractive force because it's so much closer to the proton, the nucleus, whatever you may want to defer it as. But let's not get ahead of ourselves. Why is this? Why does this make sense? How is this supposed to work? Well, there's something called Coulomb's law, which denotes force to being roughly equivalent to Planck's constant Planck's constant times the charge of 1, that would be the proton, and the charge of 2, that would be the electron, and then you put all of that over the distance. Now, things change once you start messing with ionic solids like cations and anions, but for now with what we're working with, Planck's constant denotes distance to be the main factor, and as we can see, the first 2 electrons within 1s2 are very close, but then as we go over to 2s2 and 2p6, which are over here in the second ring, they start getting further away. And now that distance causes the amount of force being acted upon them to change. And what's funny is that is everything we are doing with photoelectron spectroscopy. So let's understand, I don't have the exact values on hand for sulfur, but let's understand that the distance between the first subshell or first shell will be much larger than the second. So right here we're going to draw two lines so that we understand that there's a large distance between the two. Now we're going to come over here and we're going to do one more line about the same height, and this right here is 2s2. But why we're not going to draw two more lines, and I know this kind of just randomly throwing it out there, we're not going to draw two more lines quite yet. The reason being is because we're doing sulfur, which means we have to go out to 2p6. So we're going to go all the way up, roughly denoting that as 2p6. Now within this there are going to be 6 electrons inside of here. So I need you to understand something. This is not when we'll draw the next two, and I know you might be a little bit confused, so I'll backtrack. Here, whenever you go up, that denotes how many electrons are within the subshell. Each one of these denotes a subshell. The actual line itself is a subshell. But then how high it is denotes how many electrons are within that subshell. And then we have to talk about the length. The length is the relative, I want to say it's ionization energy, something of that sort. So the number here will denote how close it is. The further to the left it is, that's why it gets towards 1s2, 2p6, blah, 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 whatever. So right here we have the 1s2. I can't exactly draw backwards, but you get the point. 1s2, 2s2, 2p6, but then now we're going to do 3s2. Then we're going to do 3p4. Now let's take a guess why 2p6 is larger than 3p4. Well, it's obvious. It's because it's so further away with the distance that it is over here, yet it's smaller because there is less electrons inside it. The height is relative. It has nothing to do with the force. It is entirely relative. Okay? But then the actual distance, further to the left that it gets and further to the right, further to the left that it gets, means that it will be more attracted to the nucleus. Let's say our nucleus was over here. And let's say we had all 16 protons? So let's say our 16 protons were here. We can see that 1s2 is closest overall. 1s2 is right up there. But then we have 2s2, which is just further away by a large gap because of these two right here. But then we see 2p6. See, 2p6 is actually further away than 2s2. Now, I get you understand, why might that not make sense? Well, there's actually something called quantum numbers from quantum mechanics that we won't quite touch on due to the difficulty of the subject. Now, of course, you will touch on this with AP chemistry, but I'm not going to do it because I don't have the time quite yet. Well, I might touch on this in a later video. See me then. Now, let's get back to the point. Right here we have 2p6, okay? 2p6 is further away from the protons than 2s2 is, but it's closer than 3s2. So in all actuality, ionization energy, which is the energy required to separate an electron from an atom, or to say move the electron within the atom, is greater the further you get in. Now, mind you, there are a lot of different ways to understand this, a lot of critiques it has to this periodic table, but all in all, this is how electron spectroscopy works. So what can we take away? Well, let's understand something, alright? The protons and the electrons are all we are trying to measure within this. Now, of course, there are ionization energies, but those are actually just affecting the electrons within an atom, which are being attracted by the protons that are within that atom. So, I hope you've kind of garnered an understanding of the topic we're talking about. It mainly is relevant towards graphs, like the one I showed you, where it has the relative photoelectron intensity and it has the amount of photoelectron energy required to separate the electron from the protons. And as I stated, the further left you go is closer to the proton, and the further right you go is the further away. The higher up you go means that there are more electrons within that trough, and whenever you have a shorter trough, it means that there are less. Take the 1s2, which was like this, and then 2p6, which is all the way up here. They're completely different, and will have very large differences in the amount of energy required, depending on how close they are to the actual subject.